Hi, everybody. So this is going to be some practice on motion in one dimension. We're going to go over some similar concepts that we talked about in the last video, calculus in regards to manipulating graphs. Got my iPad over here, so this is, sorry if I jump off the screen real quick. So this is going to be titled 2C and 2D. This is from the old physical science curriculum. Whoops, marking on stuff. From the old physical science or AP physics curriculum that we'll be using for review. So first, let's go over P13. Assume that an object changes position with respect to time in the following way. So we're going to graph x equals 1/2 t squared. X is position, t is time. We don't know that it's meters, feet, or seconds, minutes, hours, days. We just know that it is position and time. So let's graph 1/2 t squared. So after 1 second, you will have traveled 1/2. Let's just call it meters and seconds, just for SI's sake. So after 1 second, you will have traveled 1/2 of a meter. So we will make a dot there. Then after 2 seconds, that would be 1/2 times 2 squared. 1/2 times 4 is 2. I'm just plugging these numbers into t for time on that function there. So then after 2 seconds, you will have traveled, oh darn, what did I say? 1/2 times 4, 2. 2 meters. That's showing up black. Yeah, okay. I'll use a different color next time. All right, then after 3 seconds, you've got 9 divided by 2. So you've traveled 4.5. So let's say 2, 3, 4.5. And then after 5 seconds, you have traveled 25 divided by 2 is 12.5. So you've got 1, 2, 3, 4, 5, 6, 7. Way up there. Way up there. Is that showing up? Yeah, it is. Okay. All right. So now let's go ahead and draw that graph. That should have a pretty good curve to it. That'll just go off like that. I wonder if I can erase more than just, now that'll just take the whole line out. Okay, well, let's draw that all over again, shall we? Hoped I could just erase the end of that line. All right, so it's kind of sloppy. I'm still working on the iPad penmanship, but that's going to be what we're using for that graph. It is basically half a parabola, right? Now let's graph its slope. So slope is going to be the change in position with respect to time, and we can call change in position with respect to time velocity. Weird. Okay, so we're going to try a different color. We're going to use blue for velocity. And so let's try and get the slope at each given point. Now this is going to be tricky because we're going to have to hit that just right, which is very complicated. Now if we could do the derivative, we would already be able to know what the graph is supposed to look like. But it looks like that's really hard to estimate. But here we are at 1/2, here we are at 1.5, and here it looks like it would be projected at 2.5. So let's say that the slope at that point is 1. All right. Now let's see if I can delete these. Oh, that blue dot's just gonna have to stay there. If I erase that, I erase the whole thing. So now let's see if we can get the slope at this line here. That's gonna be tricky. Let's see. There. That's really close. Okay, so kind of hard to determine the slope of that line. But we hit here, and it hits an intersection again right there at about 4. So it looks like it's got a slope of 2, rise up 2 over 1. So there you've got a slope of 2. Okay, let's try and erase those. Now, this is going to be even trickier. My artistic skills are going to hinder us here. That's not great, but we're going to roll with it. Because here we go down 1, 2, 3, and we almost hit there. So there we almost have a slope of 3. So, oh, whoops. I missed. There we go. Slope of 3. So it appears that the velocity in this case would be v equals t. And if we did the power rule of x equals 1/2 t squared, we would find the same. Bring your exponent down, multiply it by the coefficient, which would be 1/2, so 2 times 1/2 is 1. And then you decrease the exponent by 1. So 2 minus 1 is 1. So then you get b equals t. Okay, good. Now, let's move on over. Now, graph the slope of the slope. Here we go. All right, so let's graph the slope of the slope. I don't know why that typo is there, but now let's graph it. So slope of the slope in this case would be acceleration, and we still have time on the bottom, right? Now, the slope of this line over here is pretty constant, right? You would say that the slope of that line is 1. So to graph it, we would put a flat line at 1. And that would be at each point, the slope was 1. Now, if we zoom that bad boy out, this is ASCII's good old-fashioned trio. Let's get rid of those right there. But that is a trio where we have a quadratic function, a linear function, and a constant function. And that is the progression in a derivative integral pair as well. As you take the derivative, it gets more and more simple. As you take the integral, it can get more and more complex. Usually. That's not a blanket statement. Now, what is the relationship between the graph below on the left and the graph below on the right? So the relationship between the two, I gave you some thinking time there. The relationship between the two is that this is, oh, whoops. There. This is your original, and this would be the graph of the slope, because this is going to be approximately y equals 3x squared. So just like we said before, when you have something that gets more and more simple, you start with, on the position, we had a quadratic, we had a position function that was squared, then we had a velocity function that was linear, and then we have an acceleration function that is constant. Same down here, we have a cubic function that could be our position, could be velocity. Then we have this quadratic function. We have this parabola that could be the velocity to a position graph or the acceleration to a velocity graph. It is the slope. That is the relationship between the two. Now, let's focus on P14A. On the graph below, sketch the slope of the slope graph of the top graph. So we've got a blank graph down here. What we will do is we will try to graph the slopes of this graph. Now, this could get complicated. Here, let's scroll down a little bit more. Now, we have a slope that starts off quite steep, and it gradually levels off. How can I get to see there? I'll just zoom out. Okay. So we have a slope that starts really high, and at this dotted line, the slope reaches 0. It looks like something might be changing direction or something, depending on if this is velocity, position, acceleration. So then there you hit 0. Then your slope becomes negative. So we need to put a negative down here. This is the most negative the slope gets, right in the middle. And then at the dotted line, it again returns to 0. And then the slope continues to increase. And if you are catching on, that top line is a cubic graph. This is a parabolic graph. Excuse the bad parabola, but this is a similar relationship where you have a cubic function and a parabolic function. And this is the same as taking the derivative of the top. You would get a function similar to the bottom. Now let's look at the graph on the right. This, they actually put units on it. It's deaths per week. And then on the bottom, it's deaths per week per week. I don't know why that's so morbid. Maybe they knew I'd have to make this video during COVID. So on the graph below, sketch the slope graph of the top graph. Now, this could also get complicated. It's a complicated graph. So let's zoom out again. Try this. Okay. So, how can I move this? I can move that. Oh, that's great. Okay, I didn't know I could do that. So we start off with a very low slope. Let's estimate that to be 0. Then that slope gradually gets higher and higher and higher, and it's going to peak on the dotted line. And then it seems to return back down to a slope near 0. So this will again give you a parabola. I missed my dot there a little bit. Forgive the missed dot. Look, my dot got bigger. I hit it. I hit the big dot. So now you have a negative parabola. And you would estimate your change in slope when you're trying to take a slope graph. Now it's not quite as easy when you're doing a graph up here like this, because you're estimating point by point. Down below, we are estimating general trends. But here we are almost working through derivatives. Now, this was the video over 2C. Our next video will be over 2D, which is going to expand on the concept that we are going to bridge the gap from graph math to calculus math.